different types of equilibrium, and we're going to focus on two main types of equilibrium problems, but let's just jump right in, shall we? So the reality is that whenever we're writing down anything, any K expression, we're always going to have some sort of subscript down below here. And essentially what that subscript is going to do is tell us what type of equilibrium we're dealing with. For example, Kc tells us that we're dealing with concentrations. Kp tells us we're dealing with pressures. Ka, acids, bases, water, solubility product, etc. I want to focus in today, though, specifically on Kc and Kp. Now, before we do that, I want to specify what happens when you mess with equations, because a K, or equilibrium constant, is specific for any one single equation at a particular temperature. So this table right here kind of specifies what happens when we mess with an equation a specific way, and let's walk through the examples using this basic equation. N2 plus 3H2 goes to 2NH3. Now, if we ever decide that we want to multiply the entire equation by a coefficient, what we have to then do is we have to raise the K expression to that power. So for example, in this case right here, you can clearly see, if you take a look at these two right here, for example, if you take a look right here, you can see that if you compare this to this, and we asked you, hey, what is the new K for this expression? This expression right here is exactly double the expression up here. So in essence, what we've done, our N factor, if you look up here in our table, our N factor is 2. So we have to take this 6.8 times 10 to the 5th, and we'd have to raise it all to the second power. Now, you can do this kind of piecemeal if you want. You can go times 10, and that 5 raised to the 2, that's times 10 to the 10. And the 6.8, if you squared it, that would be 46.24. Of course, all you should know that off the top of your head, right? Or you can just punch this whole thing into your calculator, as most of you would want to do. This 46.24 times 10 to the 10 would be the new K for this expression, because it's exactly the double of this one. We wouldn't really want to leave this like this, though, would we? Wouldn't we want to write it as 4.624 times 10 to the 11th, right? And we'd want to shift it over. Now, let's take a look at this one right here. What have we done between this expression right here and this expression right here? Well, quite simply, we've just flipped it. So whenever you flip an equation, whenever you use the reverse of it, the new expression is just 1 over the old. So if we take this expression, the 6.8 times 10 to the negative 5, and we go, all right, that's our old K is 6.8 times 10 to the negative, or 10 to the 5th. My new K is going to be 1 over that, right? Or 6.8 times 10 to the 5th, all to the negative 1, right? If we do that, essentially what we're going to do is we're going to end up with this 1 over 6.8 times 10 to the negative 5. And again, as most of you will be able to do in your head, that will put us at 1.47 times 10 to the negative 6. So this is actually pretty straightforward. If you have an equation already, you can use one of these factors in this table to determine what the new K is. Now, remember at the very beginning here I said that we were going to focus in on two specific types of K, Kc and Kp. And I'm going to do that right now, because it is really important you understand the difference, because the majority of our problems, they'll either give you the variables in concentrations, or they'll give it to you in atmospheres. Now, if you can tell the difference, this here is concentration, and this right here is, those are supposed to be arrows. These are units of concentration, these are units of pressure. This square brackets, remember from the previous video, that's molarity. Now, if they give you a Kc, that will only work with concentrations. KPs will only work with atmospheres. They are not interchangeable. But what will often happen, as you can imagine, they'll give you a Kc, and then they'll give you a problem in terms of pressures, and that kind of messes us up. So how do we work back and forth with this? Well, it's this equation right here. So if you take a look, this right here, this expression, this right here is how we go back and forth between Kp and Kc. Now this R, you may have seen it before. This is the gas constant that we dealt with before, 0.082. Here they chop it off to 1, but 0.08206 latmas per mole. We've used that before. And this change in N, and anytime we have change in something, we always take the products minus the reactants. So what we'll do is we'll take the moles of the products minus the moles of the reactants, and this only works for gas particles. So lest I get confused anymore, let's say we wanted to find the Kp for this practice problem here. Let's do it together, shall we? This Kp, and they give us a Kc of this right here, right? So our overall equation we're going to work into is going to be Kp is equal to Kc RT change in N. Now let's talk about the change in N, because that's the most important thing. If you take a look here, then we have gas here and a gas here, and the coefficient in front of each of those is 1. So we have 2 moles of gas on this side. On this side, we have, check this out, this is a solid, right? So we have 0 moles of gas on this side. So if we take our products minus our reactants, our change in N in this case here is going to be 2. Because our product moles of gas minus our reactant moles of gas is going to be 2. So then we're just going to plug everything into our equation. So we're going to go 6.96 times 10 to the negative fifth. We're going to multiply that all by, and I'm going to put this in square brackets to realize that this is together, 0.0821. And then the units are latmas per mole. So I'm going to put them in here, although I'm not going to worry about canceling them out. And that's going to all be times our temperature. Now our temperature has to be in Kelvin, because remember all our gas problems have to be in Kelvin. And when you take this N and you square this and multiply it all out, again, you can most likely do this in your head, but you're going to end up with a value of 0.052. Now this is what you would use if you're dealing with atmospheres. And if you take a look here, I'm not going to, and I think we said this before, but for some weird reason, well, actually I know the reason, because it gets really messy, they don't really require you to put units for your Kp or Kc, but this is how you would solve for your Kp if they give you Kc. Well, what if they did the other way around? What if they gave you a Kp? Now, if you notice here, they give you a Kp, all these are gases, right? So likely if you're doing a problem and you had a Kp, you'd be dealing with atmospheres, right? So what if we wanted to go the opposite route? Well, the same deal holds here. We could still write our Kp expression, right? So couldn't we go Kp equals Kc RT change in N? Now, the only difference is that we're solving for this. That means they must give us all the rest of the variables. And although I like rearranging in advance, couldn't we just do this and plug in numbers here? Couldn't we put a 2.40 right here? Couldn't we leave our Kc as the variable we're solving for? And then for our R, couldn't we go 0.0821? I am not going to put the units in this time, sorry. Times 373. All of that, by the way, would be raised. And if you take a look at the number of moles of gas, which is probably important here for the change in N, right? We have 2 moles of gas on this side, and on this side we have 3 moles of gas. So if we do our change in N, it's going to be 2 minus 3, which gives us a -1. That means we're going to have a -1 out here. And if you rearrange and solve that, our Kc is going to end up being 73.5, which is a crazy high K value. Now, just a quick recap here. If we go back up here to all of these variables right here, we're going to focus in on Kc and Kp for the majority of our problems, because that's what we're going to work with the most. But if you take a look at the subscript just kind of gives us a more of identifiable version of what type of reaction we're dealing with. That's all I have for right now. We'll see you next video.